for the last lecture of this morning. So it's a pleasure to welcome Luis Garcia from UCL, who's going to talk about his ongoing project with Nicolas and Pierre that we've been hearing about this week in the Eisenstein lectures. So he'll talk on an Eisenstein cocycle for imaginary quadratic fields. So,
thank you very much. And I'd like to start by thanking the organizers for inviting me. And sorry, I'm just trying to get to see. I just realized that when I go full screen, I don't see Zoom anymore. One moment. Maybe I'll just keep it like this. That's okay. So yes, thank you. And it would really have been a pleasure to visit Montreal in person. I wish I would be able to have been there. I also want to apologize for other lecturers, especially those I haven't met, for not being able to attend the lectures. I think I'll be able to attend more for the rest of the program. Right. So let me explain what I want to talk about. I have planned this talk as a complement to Nicolas' series of talks. So I'm not going to be talking so much about somehow the big picture, but rather I will go into the details of the cocycle for imaginary quadratic fields. So the idea is that Nicolas has been talking about constructions for additive and multiplicative groups and also for elliptic curves. And I want to focus on the case of elliptic curves with Cn. So I will explain two results. The first one is the following. We're going to fix an imaginary quadratic field K throughout the talk. And you pick a prime ideal P, and then I will define a cocycle for the group gamma 0 P. And the values of this cocycle lie in a space of polynomials in Kronecker-Eisenstein series. So that's the first result. And the second result is that this cocycle can actually be evaluated on homology classes coming from field extensions. And the result has to is essentially given by partial zeta functions. So these two things combined give formulas for critical values of some L-functions of extensions of K in terms of Kronecker-Eisenstein series. So these are not the first results giving such an expression. There is the results of Colmez, who proved formulas of the sort I just described using Shintani's method, but only for certain critical values. And he conjectured that they should hold for all critical values. So in that sense, we are generalizing his work. And well, so Colmez used Shintani's method, and our proof is quite different. Instead, we're going to use equivariant cohomology, although that I won't really talk about equivariant cohomology because the constructions are so explicit that one can just introduce the differential forms. And it's basically a construction using Eisenstein series and using the geometry of the symmetric space of the C. Okay, so let me start by, I want to start by stating the first result. So as I said, we fix an imaginary quadratic field K and embedding sigma of K into the complex numbers. And I'm going to let O be the ring of integers in K. And now here is the classical Kronecker-Eisenstein series that appears, for example, in the book of the famous book of Bay on elliptic functions according to Eisenstein and Kronecker. So it depends on two non-negative integers P and Q, and it's just given by that expression. You sum over some fractional ideal, which forms a lattice in C, and you have to stay outside of, so Z has to be a complex number that's not in the image of this ideal. So as usual, this sum converges for real part of S large enough, and it has analytic continuation that's regular at S equals 0. And that's the value that we're going to care about. And these functions have classically have algebraicity properties. So let me explain. Maybe I can outline briefly why. So this is basically the following thing. I'm going to let E be the elliptic curve with Cm defined by C divided by O, and I pick up prime ideal P of O. Can this be read? Can people read this? Hopefully you can. Right. So then it's a little bit easier to deal with the following modification of the Kronecker-Eisenstein series. I'm just going to do the simplest case. So these integers P and Q are just both 0, and then I'm going to take this linear combination like this. And if you do this, then it's very easy to show that this differential form, where omega infinity is the period of this CM elliptic curve, has logarithmic singularities. And in fact, you can show that it's of this form, where this lies in omega 1 of E minus the P torsion. So it's easy to show an equation like this, and then where GP is a certain meromorphic function with zeros and poles only on the P torsion. So once you show this, then the algebraicity properties follow quite easily, because you can take GP to be actually defined over Q bar. Right. Okay, so the cocycle is going to consist of polynomials in these Kronecker-Eisenstein series. So let me introduce those. So I'm just going to take products of n Kronecker-Eisenstein series. So I pick n fractional ideals, and I also have to pick a multi-index, well, 2 multi-indices, and then I form the product that you see there, case ij. And this depends on n complex numbers z1 up to zn. And more generally, you can define a similar quantity for a lattice. You pick a lattice, an O lattice in k to the n, and then you can find some direct sum of n fractional ideas that has finite index in this lattice, and you make that definition. And again, we're interested in the values at s equals 0. And we're interested in the space generated by translates of this of these functions by there is an action of the group SLMK on this space. So basically, if you have a matrix in SLMK, you can act on the argument and on the lattice, and you obtain another such function. So this is the space F. And finally, I'm going to introduce something that I call a p-smoothing, where you fix a prime ideal, prime norm, in fact, and then we introduce this modification. So again, it's a similar modification to the one I gave in the first slide, where I was describing that it's a little bit easier to see the algebraicity for these modified Kronecker-Eisenstein series. So you modify sort of by changing only the first, the lattice along the first coordinate. Okay, so right. So the statement that what I'm about to state is that these series can be combined to a homogeneous cocycle for the group gamma 0. And here is before I state that, let me remind you what this means. if you have a group gamma and gamma module M, then homogeneous n cocycle is a map from n tuples of gamma to M, satisfying these two properties here. So you have an equivariance property. So here, yeah, I mean, basically you have this equivariance here. And you also have this condition that really says that this is a closed cochain in the complex computing group cohomology. Okay, so I can now state the first result. So first of all, if I'm going to introduce one last bit of notation, if you pick a matrix, an n by n matrix with coefficients in O, you can define this object that I call dPij, which is given by this expression here. So you let A act on both the argument Z and on the lattice O to the n. And the expression involves A inverse. So if A is not invertible, then I just set it to 0. Okay. So here is the first theorem. So I want to define a cocycle, and what I do is the following. I start with n elements of gamma 0 of P, and I form a matrix that I call A gamma attached to that tuple, which is the matrix that you get by considering the first columns of each of gamma 1 up to gamma n. So again, that's a matrix with coefficients in O. And now that could be invertible or not, but in any case, we can define a map that I call EP that to such an n tuple attaches this quantity here. Okay, so you can see that here I haven't explained this, but so in fact the cocycle is valued in the space F, which is basically the span of all translates by SLNK of this Kronecker-Eisenstein series. But it's also, you have to allow for coefficients to be able to do this for general, I mean, to be able to obtain results about arbitrary critical values of partial beta functions. So here, EIJ, so EI is just the product of E1, I1 up to EM, IM, which you can think of as living in the symmetric, in the fleet symmetric power of C to the M. And similarly for EIJ will be e to the I times e to the j conjugate. Right. So here the sum is over all multi-indices whose so here I
n-1 cocycle, Luis.
It's a homogeneous n cocycle.
But it's degree n-1. I mean,
yeah, it's degree n-1, but when you use homogeneous cocycles, then
oh,
yeah, you're okay. Yeah, you're right. It's like I understand. Okay. It's a little bit confusing. It's an n-1 cocycle, but I think often people would call this a homogeneous n cocycle, even though it defines a n-1 cohomology class.
Okay, thanks. I didn't know.
Maybe
that.
should I have said that? Maybe I okay.
No, I don't think so. I think that's called an n-1 cocycle.
Okay. Oh, hi, Samit. Okay. Yeah. Fine. Sorry about that. Yeah, you're right. You're probably right. Okay. So that's that. Yeah. Okay. So that's the statement. So it should be. Okay. So I'll remove the question mark. Okay. Right. Okay, so let me explain how the proof of this is going to go. So the idea is the following. We're going to work on X, which will be the symmetric space of S and C. And I'm going to pick a vector in C to the n. And I am now going to define the following, an Eisenstein series that I denote by E tilde, which is an n-1 form on X. So this is the space of differential n-1 forms on X. And it will satisfy a number of properties. So first of all, it's a closed differential form. Second, it has an equivariance property. Like this, where G is a matrix is in S and C. And also, it will be rapidly decreasing at certain cusps. And in fact, this will only be true for generic B. I will be a bit more precise later. Okay, so basically we will be able to show that the constant term at certain cusps vanishes. And then the relation with the cocycle is that given an n-tuple in here, there exists a modular symbol that I will call delta gamma, which is a submanifold of the symmetric space X. And if you the cocycle that I mentioned in the previous slide, evaluated at gamma, it's just given by integrating this Einstein series. And right. So this integral converges for generic B because for such V, the Einstein series is rapidly decreasing on the modular symbol. And because of these first two properties, the fact that the Einstein series is closed as a differential form and this equivariance property, these two will imply the cocycle property. Okay, so that's the strategy, and from our point of view, this is one reason why we only work with smooth cocycles. Okay, so the main thing to do to define this Eisenstein series is essentially defining the test vector at infinity, which is somehow the where most of the content is in the construction. So let me explain how this will work. So we're going to consider X, and on X we have a vector bundle that I will call V, which is just the trivial vector bundle with fiber C to the n. And let me remind you that X is S(C) divided by SUN. So X is actually isomorphic to the space of Hermitian metrics on C to the n with determinant 1. And the isomorphism just sends a coset by two this matrix here that I will call H. Right. So now, so you can think of a point of the symmetric space X as a Hermitian metric on C to the n. So you can think of V as carrying a tautological Hermitian metric. So, namely, the metric on a certain point over X is just that metric parameterized by that point. And therefore, as there is a construction due to Matei-Quillen that says that there exists a canonical Tom form that I will call phi MQ. So this is a form of degree, the real rank of the bundle V, so 2n, and it has the property that it's closed. And if you integrate on any fiber, you get 1. And it's also functorial. And there is also a canonical transgression of this Tom form that is behind a lot of what Nicolas has been discussing in his lectures, that I will call psi, which has degree 2n minus 1. And using it, one can take its Marin transform, which is given by this expression. Sin q, t to the s, dt. And one reason one does this is that zeta and q of 0 is a transgression of phi. Right. Okay, so as you can see, let me go back, sorry. These are forms that whose degree is a little bit too large, and they also live on the total space of the vector bundle rather than on X. So the next step is we do the following. So let me have this here again. If you take a vector V, you can think of it as defining a section of this vector bundle. And for V in here, we're going to define the following thing. We pull back by this section V star, not the whole form that I just described, but a certain component. So let me explain what I mean by this. If you have a form, here you have omega 2n minus 1 of the, and here you have some form of degree 2n minus 1, you can always write it in the following way. So basically, you have these forms dz and dz bar, and what I mean is that we're going to take the component corresponding to this. So it's really the component that where the it's really the part that corresponds to the components in the vertical direction just being given by dz1 wedge dzn. And as a result, if you do that, you obtain an n-1 form on X. Okay, and this is our main character. And in fact, this is can be explicitly given. So if there is no need to really go through all this construction of material and fluid, I'm going to tell you exactly how the form looks like. So remember, we're thinking of points of the symmetric space as being given by Hermitian metrics. So sort of by Hermitian matrices, let me call them the entries, let me call them Hij. Then each Hij defines a function on the symmetric space. To a matrix, you attach its ijth entry. This is a smooth function. And you can also differentiate it, and you obtain a one form on the symmetric space. So now, let me introduce this. So you can multiply the matrix H by B and take the ith coordinate. So you get this expression here, and the same for BH. So this is a smooth function on X, and this is a one form. Now I'm going to form an n-1 form that is a polynomial in these quantities here. So you sum like this, and you pick HBI, and now you wedge all these guys except for the ith one. So remove this from the wedge. DHB. Okay, so this is a n-1 form. Nice. And the form I just described to you, I just described to you can be just this simple expression. You take P of V conjugate, and you divide by this expression. Okay, so it's given by a completely explicit expression in differential forms in the symmetric space. Right. So let me describe what the properties of this form are, because this is what's going to give rise to our so let me just introduce notation. This will be just evaluate that zero. So first of all, it's equivariant. Yeah. This sort of follows from the functoriality of these multi-equivalent forms. Second, it's closed. This is not completely obvious because the original form that I denoted eta sub mq is closed because of well, that's part of multi-equivalent theory. However, now we're picking a certain component, and it's in principle it's not obvious that it's closed, but one can just compute it, for example, using the expression I gave before, and you'll see it's closed. And I can also consider a version with coefficients. If you take two non-negative integers, you can introduce a form that I denote eta pq of v, which is an n-1 form. valued in the space BPQ, which is just this tensor. And this is given by the following expression. If you take this form and you evaluate it on two polynomials, so these two are polynomials on C to the n of degrees P and Q. Then it's given by the following expression, which will look familiar to anyone that has read any of such papers. So basically, the polynomial P acts by differentiation, and the polynomial Q acts by multiplying by sort of conjugates of the coordinates z1 up to zn. So in such work on the cocycle for totally real fields, the polynomial Q doesn't appear because, well, there is essentially only one parameter, but one can incorporate it like this, and one obtains a form with essentially the same properties that I just pointed out for eta. So it's still closed and equivariant, and it's the form that we will use to form our Einstein series. And finally, there is one more property that says you take the torus of diagonal matrices inside SLNC, and you obtain a submanifold of the symmetric space. Just from the embedding of T into SLNC, you obtain an embedding of T mod T intersection, the maximal, the maximal compact SUN inside X. And this is just given by, it's a manifold of dimension n-1, real dimension -1. So the dimensions match, and you can integrate this quantity here. And let me just take it, evaluate it at these sort of monomials given by these expressions here. Then this is given by a easy non-zero constant times following expression ik factorial over 2 times bk to the conjugate, and here you have bk ik plus 1 and bk to the 2s. Right. So this is so this is the statement, and this again is not difficult to prove. The proof uses the functoriality of multi-equivalent forms together with the fact that so you're restricting this form eta pq to a certain submanifold of T, and that submanifold parameterizes certain metrics on C to the n, and namely it parameterizes the metrics such that, so when you restrict V, the vector bundle V to this submanifold, the metrics that you get make the decomposition into using the coordinate lines of orthogonal decomposition. So those are the metrics making this decomposition orthogonal, and then you can the expression for this differential from eta pq becomes much simpler when you restrict there, and then you can just integrate. Okay, so that's what I want to say about these forms. And now let me move on to Eisenstein series. So to define this Eisenstein series, you pick a lattice, an O lattice in K to the n, and I'm going to define the tilde of that lattice to be just given by taking the form I just described and averaging over the lattice. There is also this translate by this vector p. This is a n-1 form on X. And okay, I mean, you can of course do the same version for with coefficients, but maybe I won't write it every time. And if your vectors happens to be if your vector p happens to be a rational vector, then this is invariant under a certain arithmetic subgroup, namely if you look, for example, at this, if you take it out this O to the n, then this is an n-1 form on X that's invariant under gamma 1 of V0, which you can think of as an n-1 form on X modulo gamma 1 of V0. Okay, and because of the properties of the form eta, this Eisenstein series is closed when you set x equal to 0, and you can also consider its somehow its smooth version, where you define EP of V to be this expression here, EP of V, evaluated at 0 of this lattice. So you're just modifying the lattice O to the n by making it a little bit larger in the direction of the first coordinate, and we're subtracting this quantity here. And what you find if you do this is that EP of V has vanishing constant term. At certain cusps. Okay, so let me now describe briefly modular symbols, which is where we want to integrate our Eisenstein series on. So if you start with n matrices in gamma 0 of p to the n, let's assume that the matrix that you get by taking their first columns is invertible. Then you obtain a modular symbol, which comes from the following metrics. So these are the Hermitian metrics, such that the decomposition of C to the n into the lines. So I'm assuming that this is an invertible matrix. So I can think of these as being a basis of C to the n. And I want this decomposition to be orthogonal. So that gives me a submanifold inside X. and that I will call delta or gamma. It's also of the same form as before. You have a certain torus, and it's of the form of this one. Right. So the point of the smoothing is that this series is rapidly decreasing. On delta gamma. And because of what I said about the Einstein series being having vanishing constant term at certain cusps. And when you integrate it on this, you obtain our cocycle. So basically, the way this works is that all the work is in being able to integrate eta, and it's the formula I gave before for integrating eta on a submanifold of the form on a modular symbol like this. So this sort of follows trivially from the properties of eta for gamma and 0. Okay. Right. Okay, so that's basically what I wanted to say about how one can define an Einstein series that gives rise to this cocycle. And I want to now move on to the second main result, which has to do with partial zeta functions, well, not of K, but of finite extensions of K. So I need to introduce some notation to state the result. So I'm now going to consider degree n field extensions of K. I will consider an extension called L. N denotes the normal map from L to K. I will take ideals A and F of the ring of integers of L. I also have a group of units attached to F. It's the units of OL that are congruent to 1 mod F. And one can define a certain partial zeta function given by this expression here. Again, this has analytic continuation. We care about its value at s equals 0. And moreover, we are going to consider smooth versions of these functions. In fact, we're going to consider a double smoothing. So you see, you pick two ideals, P1 and P2, and then the first smoothing looks similar to the smoothings we have been considered. You take a linear combination weighted by the norm of the smoothing ideal, but then there is a second smoothing given by that expression in the last one. Okay, so I just wanted to point out here that these functions appear. These zeta functions appear as when you try to express Hecke L-functions. So, so if you take a Hecke character of this form, let me take it like this. So, chi is a Dirichlet character of L, and omega is a Hecke character of K of weight PQ. Then you can consider this Hecke character phi, and the L function of this Hecke character is a linear combination of zeta functions of this form, -1 minus p, q, a, s, where ai runs over representatives of the Ray class group of conductor F. Sorry, so I should say F is the conductor. Let's take a character phi. And similarly, you can consider a smooth version of this L function. So you can multiply by these local L factors. At P1 and at P2. And this will be a linear combination of these smooth zeta functions that I introduced above. -1 -2 from a Q of AI 0. Okay, so if you're able to express each of these partial zeta functions as a polynomial in Kronecker-Eisenstein series, then basically you have done the same for these L functions with this smoothing coming from multiplying by the inverse of these two local factors of P1 and P2. Right, so, okay. So I'm going back to the relation with the cocycle, I'm going to pick an isomorphism of L with k to the n, a basis of L. You denote by sigma 1 up to sigma n the embeddings of L into C that extend our embedding sigma. And well, here is some additional notation. V0 is the point where we're going to want to evaluate our Eisenstein cocycle. It's the image under alpha of 1. And there is also a lattice, the lattice lambda there. I'm also going to pick a generating set for the units, for the unit group UF. So this is a unit of rank n-1, and I pick units that generate the free part. And this expression is going to involve permutations of length n-1. So I'm going to define these n-1 tuples there. And finally, here are some smooth versions of the Eisenstein cocycle that I introduced before. So again, there is some smoothing involved. Okay. So here is the main theorem. So we fix the conductor F, and we pick representatives for the Ray class group, A1 up to AR. And after that, we pick our smoothing. I will explain a little bit more about this in a moment. And the formula says that you can find prime ideals P1 and P2 such that the smooth zeta function using P1 and P2 is given by this expression in the smooth Eisenstein cocycle. Right. Yeah. So in particular, this expresses the smooth partial zeta functions and therefore the non-smooth ones as well as a polynomial in Kronecker-Eisenstein series, which was done under some restrictions by Colmez. So this is the generalization I was talking about before. Right, so this is valid for all weights P and Q. Okay, so let me explain briefly how one proves this theorem and why one needs a second smoothing. Okay, so right, so we had this extension of degree m of k, and we had our isomorphism of k to the n with L. Then you obtain a map from L1 to S(k). This is just a group of non-zero elements of L of norm 1, relative norm 1. Okay. And corresponding to this, you obtain an embedding of something that I will call XF, which is this expression here, UF. So C1, and then you have the compact part. This embeds into a quotient of X, where gamma is the intersection of gamma 0 of P and gamma 1 of V0. So remember V0 is this. Go to the end. Okay, so again, this is an n-1 manifold. It's basically, actually, it's an n-1 close. And if you integrate the Eisenstein series I introduced before, you also have to pick ideals, polynomials for your coefficients. So you just choose the norm to the P and the norm conjugate to the Q's power. And there is lambda. Lambda is alpha of F A inverse. Then this expression here is essentially because of the because of the formulas for eta I gave before. This is given by J. It's this matrix that appeared in the main statement times this smooth zeta function. So this is just again, it sort of follows easily from the properties of eta, which is that test vector we're using at infinity to construct our Eisenstein series. And now the question is, okay, we have this Eisenstein series. When we integrate it on these cycles xf, we get the zeta value, the smooth zeta values. When we integrate it on modular symbols, we obtain these polynomials in Kronecker-Eisenstein series. So how do you get our result? And the answer is that you just you can just move the cycles inside the symmetric space. So let me just explain how this works for n equals 2. So here is a picture of the symmetric space. So for n equals 2, the symmetric space is just the complex numbers times the real numbers. So you can picture it like this. And now, if you have a geodesic segment like this, so here this is an extension of degree 2, and so we are interested in picking a unit of norm 1 that's non-Gaussian, and integrating our Eisenstein series on the geodesic segment from a certain x0 to its translate. If you do this, then, well, you can do the following thing. Here is a point on the boundary of the symmetric space corresponding to a certain cusp that I will label by E1. And here is the cusp labeled by UE1. And now you also have a modular symbol joining these two, like this. And, well, let me denote this by U. So if you know that this is rapidly decreasing, along these cusps, E1 and UE1, then, well, when you integrate EP of V0 from here to here, you obtain this integral one, maybe with a sign. So this segment here, sorry, this segment here is what is the modular symbol labeled by 1 and u. You obtain these things because basically, well, it's closed and you use Stokes' theorem and the other sides cancel. So that's how you proceed if you happen to know that V0, that EP is rapidly decreasing. Unfortunately, in general, it doesn't have to be. I mean, for it to be rapidly decreasing, you need a condition that basically V0 does not lie in either in the line spanned by E1 or in the line spanned by UE1. Or let me do. Let me explain one more case. The case n equals 3. In this case, you're basically integrating. You pick two. You pick 2 units of relative norm 1 that generates the free part. So it equals and then you have to integrate along a cycle that looks like this. So there's x0, ux0, dx0, and udx0. And what you do, and this is where the symmetric group comes in our picture, is that when you're there is a decomposition of this square into 2 triangles, and in general of a cube into of a cube of dimension n into simplices indexed by the symmetric group of length n. So you can just take this cycle, each of them, and move it to the boundary. So here is how it looks like for the first triangle. And now here is a modular symbol that you label by E1, UE1, and UV-E1. And you have a homotopy where you can just really push this triangle to this triangle on the boundary. So this is these vertical arrows stand for an explicit homotopy, which you can do for any n. And again, you obtain well, that this integral over this triangle here, Vx0 equals plus minus the integral over this. Again, assuming that if P of V0 is rapidly decreasing. So for this, and I'll finish with this, I still have 1 minute, I think, maybe 2.
Take your...
Right, so this is, let me just say, this is guaranteed by the P2 smoothing. So this is the issue, that these cocycles are valued in a space of functions that are not defined everywhere. So if you want to evaluate them somewhere, you have to make sure that you are inside the domain of definition. And you can force this doing an additional smoothing. Maybe I'll just say that the condition, so maybe I'll just spend 2 more minutes if that's okay. So EP of V0 rapidly decreasing is the condition that V0 should not be part of any plane that you can, for example, in the case of n=3, any of these planes generated by E1, UE1, E1, UV, E1, or basically the planes labeled by the side of this triangle, or UE1, UV, E1. Should not be here. And this is, okay, maybe I will just explain this. There is a lemma that appears in a paper of Colmez that lets you see how this works. If you have a finite number of k-linear forms, finite set of k-linear forms on L, and you fix some fractional ideal, you can always find prime P, which will be our P2, such that phi I is non-vanishing on any of these cosets where L belongs to this. So basically, you're trying to evaluate a certain sum over a fractional ideal A, but by introducing this smoothing, you can think of it using some sort of distribution relation as a sum over A multiplied by P2, and you're just adding over the non-trivial translates of A by elements of P2. You can always find such an ideal P2 such that a given set of linear forms doesn't vanish. And this means that, in particular, you can take the linear forms defining these planes in the case n=3, or the hyperplanes in the modular symbol for larger planes. So once you do this, you're guaranteed to be evaluating the cycle somewhere where there is no, where all the Kronecker-Eisenstein series are well defined. And I'm sorry I went a little over time. So yeah, I think that's it. Thank you.
Thank you very much, Luis. Are there any questions or comments? If so, no one is raising their hand. So I wanted to maybe ask a bit something like the question of Samit in the previous lecture about whether these constructions of yours give insight into the p-adic interpolation of these Hecke L values, and in particular, whether you see any applications to Hecke L-functions in the when the prime P is inert in the
so I think that p-adic interpolation should follow for these L-functions. In fact, Colmez remarks that in the Colmez next paper, he remarks that if you could prove what he's proving for other ways, then his arguments for p-adic interpolation would also go through. So I think in some sense, I mean, I haven't checked the details, but it should probably be okay. I am not so sure about what happens when P is inert. In particular, I don't even know how much is known about the original Kronecker-Eisenstein series in that case. Yeah, so I can't say much about that. So.
Are there any other comments or questions for Luis?
Hi,
sorry, Mike.
It's not a question, but to I don't know, let's say, anything about p-adic L-functions, but I would be interested if someone who has some, with respect to Samit's question, because somehow we reduce everything to the one-dimensional case, and if I understand correctly, in that case, thanks to work of Banai and Kobayashi, the answer to your question is yes. So so I would be yeah, I think this is the right formula that to try to extend this to higher dimension. That's so if someone is working on that, then it would be nice to discuss.
Yeah, the setup seems so well adapted to p-adic interpolation. Right? The whole construction that you have. I mean, with these torsion sections, which one could conceivably vary in.
To confront the two last lecture, I would say that what Johannes gave is really a powerful method that is much powerful, I guess, to deal with rationality statement and so on. But one slight difference, I think, is that this method allows to decompose into product of some simpler object. That's exactly the relation with the Sharifi lecture or Le Couturier lecture. I mean, going to infinity and integrating on modular symbol allows to pass from a problem which belongs to an n-dimensional problem to a product of one-dimensional problem. So somehow, when the question is easier in the dimension one, then might expect that this can be useful in that setting. Yeah.
In fact, maybe I can ask a question, which is that in the paper of Charollois and Dasgupta on an integral refinement of the cocycle, they have an application to multiplicities of zeros of the p-adic L-function that they are interpolating. Which, for example, I wonder if one can imagine a similar application here, but I don't know if someone like Samit would know off the bat.
Yeah, I mean, I think yes. I mean, once you build a cohomology class valued in measures and you have the p-adic L-function, then this order of vanishing that you're alluding to is purely on the homology side. So you produce the p-adic L-function as the cat product between the cohomology class that you produce and then some homology class, and then you sort of all the analytic aspects are already taken care of on the cohomology class that you produce, and then the vanishing arises from the sort of the homology side. So that's more formal and algebraic. So I think it has a good chance, and it's just comes from the way that you pair you make a homology class out of these units that you've put together. So I think that should go through.
But what kind of statement would you be proving that would be interesting?
Yeah, so it would something just about trivial zeros. I don't know. So it would be order of vanishing of a p-adic L-function whenever you have trivial zeros. So yeah, I don't know exactly what the L-function is that we're constructing, but once you have constructed the L-function, you expect trivial zeros, then I think you can account for the trivial zeros with this.
And it's okay.
I think you have lower bounds, right, for the zeros in your.
Exactly. I mean.
Yeah, exactly. But there's always
Right.
Yeah. Are there any other questions or remarks? Well, if not, I'd like to thank again all the speakers for this morning's session, for all their lectures. It was great. Another round of applause for all the speakers.